Thank you so much for that kind introduction. Hi, everyone. I'm Sigrid, and I'm an assistant professor here in the Department of Aeronautics and Astronautics. And I'm here to talk to you about my very favorite topic, which is, and I hope by the end of the talk you're going to love it as much as I do. So, show of hands, who's heard of a dinosaur? Great. Next show of hands. Who can tell me why the dinosaurs may have died out? In the front. Meteors. How so? What happened? In the very back, blonde. That's right. That's right. Excellent. The reason why we're all here today and we are the apex predator is because the other apex predator from 65 million years ago was killed by a really big asteroid. Okay, it's not the only theory out there about why the dinosaurs went extinct, but it's certainly the most prevalent and the most well-supported scientifically. Okay, last question. How are we all here today? How did life form on Earth? Bacteria coming from possibly where? Space. You guys heard of Carl Sagan? We're all made of star stuff? Yeah. Very controversial theory. However, again, we're starting to think that maybe the reason we're here today is because as meteoroids were traveling through interstellar space, they eventually found their way to Earth. As they found their way to Earth, they were being irradiated by these neutron stars. Okay? And what happened was, not to get into too much of the chemistry here, is that what happened is it preferentially selected for something called the chirality. Okay? All of us here on Earth have something called this left chirality. So now people are starting to look and say, maybe life on Earth actually came from meteors too. But this is an engineering day, and I'm an engineer, so why do you think maybe I like to study meteors? Dinosaurs is awesome, life on Earth, geology. What's maybe an engineering focus to studying meteors? Can anyone guess? What was that? Landing on one, excellent. Anyone else? Yes? Excellent, that's right. I like to blow things up. I like hitting things with other things, and guess what? These things hit my satellites. So the whole reason I started looking at meteors and asteroids years ago is because they were kind of a pain. When I was trying to do something, these meteors kept getting in the way. Either they were making clutter in my data or they were hitting my satellites. So now, we at Stanford are actually trying to solve the problem of how do meteoroids interact with spacecraft? Can we build spacecraft to go rendezvous with asteroids? And thereby get rid of the problem so that all of you young budding engineers don't need to worry about it. But first, because Hollywood loves this topic, let's play a clip from a really bad comet movie. Has anyone seen this movie? So there's a lot of drama, doom associated with what I do, and Hollywood loves this. Hollywood loves this. I never even heard of this before. 2 days ago. So why do we do it? As I mentioned, we like to study these to protect our space assets, to build spacecraft, to go do exploratory research. One of the things I wanted to be when I was really little is I wanted to be an astronaut. I wanted to go and build spacecraft and go journey through the solar system. I haven't been able to do that, but I like studying it to understand when we send those spacecraft out, how are they going to be affected if they come across things like a meteoroid or an asteroid? So if you'll forgive me, I'm going to go through kind of an outline of the presentation, and I want to talk first about the little ones. Dust and meteoroids. When I say little, I mean tiny. Think grain of sand. Go to the beach, pick it up. That's about the size limit, and then smaller, okay? Big ones, asteroids and comets. So about this big to things bigger than this building, things bigger than Palo Alto and Stanford, okay? And then we'll summarize. Okay, so just to start off with, what am I talking about? Well, first, there's dust and meteoroids. Again, think grain of sand or smaller. These can be either rocky, okay, so stony, they originate from asteroids, or they can be icy, they come from comets. And the only distinction between the two is the fact that meteoroids tend to be a little bit bigger in size, but really they're basically the same thing. Nicholas, one of my students who just defended, has some meteoroids that he's going to be passing around These aren't really expensive, but I ask if you could please don't lose them, because I only have a few of them, just to show you about the size of what we're talking about with meteoroids. And again, asteroids and comets, these tend to be the bigger things that can hit us. Now, again, lots of controversy, because what we're finding just in the past few years is that there's not actually a big distinction between an asteroid and a comet. If I were to ask you, what's the biggest difference between an asteroid and a comet? What might you say? Comet has a tail. Excellent. Anyone else? Comet's made out of ice. What if I were to tell you that some asteroids have tails? How would you now start to distinguish an asteroid from a comet? What it's made out of? What if I said that the density of comets is a little bit higher than what we previously thought because of these spacecraft rendezvous missions? It's getting a little bit more difficult to tell, right? Okay? So yes, I'm going to use the distinction, comets have tails, but please know that our latest research as of just a few months, 2 years ago, says that this line is a little bit more blurry than we had previously thought. Okay, the good, the bad, and the ugly. I'm dating myself here. This is an old movie. Let's talk about why asteroids and comets and meteoroids are good, why they're bad, and then why they're really ugly, which you already know because you answered the question in the beginning. Good impacts. Well, we used to think years ago that these asteroids and comets would hit Earth and actually kind of suppress continental formation on Earth. So we actually thought that they were a detriment to us being here, because of course we live on land, we need land to live. Between 3.5 to 2.5 billion years ago, Earth went through this period of heavy bombardment, meaning the solar system was basically getting cleaned out like a vacuum cleaner, okay? Earth was being hit quite a bit, all right? What happened was, as they're now realizing, is that as opposed to it actually suppressing land formation, that these asteroids would hit the Earth, and yeah, suppress it locally, but then underneath the crust, this volcanic activity, what was actually forming the continents, got to spread out a bit more, so that when the land actually came up, it was much bigger, more solid, more able to support life, our type of life, okay? So one reason why we should be thankful that asteroids and comets hit the Earth is because we think now that they're the reason why we have so many continents. And as we all mentioned, it's also possible that meteoroids are responsible for life on Earth. So here's the Earth. This is just an animation showing that the Earth every few months or so goes through a period of shower activity, where it basically gets bombarded by a higher flux, so more particles, in our solar system. And this causes what we call a meteor shower. Who here has heard of the Perseids, the Leonids, right? It makes the news a lot. What you may not know is that, yes, those are the ones you can visually see. They're very exciting. They're these big streaks across the sky. Every morning, we go through what you would call a shower. You just can't see it. These are particles that are about a microgram. So again, think microgram, really tiny. So you can't visually see it, but we can detect it with our instruments. And what we found is that it's actually not the Perseids and the Leonids that are most threatening to Earth or could cause life on Earth, but it's actually these sporadic particles. The bad, as I mentioned, satellites, particularly my satellites, have been hit, okay? This is bad. How much do you think a satellite costs? Several $1 billion. Are the meteorites getting around? Think about that tiny meteorite, whoever has it, taking out a $1 billion satellite. What do you think the satellite owners are going to say? They're not happy. And when they're not happy, the first person they go to is the engineer. Why did my satellite fail? And at the end of the day, a lot of times we actually don't know. It's one of the reasons why we do what we do here at Stanford. One of the things we're trying to figure out is when these meteoroids hit these satellites, what can happen? Not just puncturing through. We know a little bit more about that. But can it ionize itself and create a plasma, the fourth state of matter, these ions and electrons, and can they emit and then cause electrical anomalies? This we don't know about. This is what people are studying today. Humans get hit. How many people have heard about this? This is a disturbing image, so I'm sorry to the children in the room. Elizabeth Hodges, back in the 1950s, it's a very interesting story. She was sitting on her couch, the story goes, watching TV, heard a big crash. Big thing comes through her roof, bounces off the table, and hits her in the hip, okay? Everyone thought she was crazy. There's no way she got hit by a rock falling from space. Turns out it was actually a meteorite. Gerrit Blanc in Germany, walking on his way to school in 2009, same thing. I don't know if you could see this. It's hard to see, but there's a very little cut on his hands. He said the same thing. A rock came from space. It hit me. Everyone's like, you're crazy. Turns out they did some spectroscopy on the rock, and the rock indeed was a meteorite. It hit him on the hand and then bounced off. Tiny little thing, tiny little thing. Other stories about doctors' offices where meteorites crash through. I mean, every once in a while, if you look in the news, you'll find a report of either someone claiming to be hit, or an actual hit, or something, again, coming through the roof of a building, which is far more likely. And as we all know, how I start off the talk, ugly impacts. This, when we first started really thinking that the reason why the dinosaurs died was because of an asteroid impact, the funding increased. This is good. Funding increased to go find out all the objects out there that could possibly hit the Earth. Okay? Then, as they started finding more and more objects, and as they kept saying, well, this one's not going to hit, this one's not going to hit, this one's not going to hit, what do you think happened to the funding? And that's where we are right now, actually. There's only 3 programs in the world that are characterizing all the objects out there that could potentially hit us. Now, having said this, as we know, this was caused, we believe that the dinosaurs' extinction was caused by a really big impact, 15 kilometers or so, although it's hard to actually gauge. Think of a 15-kilometer asteroid hitting the Earth and what that's going to do. As the girl in the back said, it's not just what's going to happen locally, but it's going to cause a big dust cloud, it's going to obscure the sun, and it's going to cause basically widespread devastation. But this occurred 65 million years ago, and to our knowledge, nothing this big has hit the Earth since. Does anyone know why? Why were there more bigger things hitting the Earth in the past than there are right now? That's right, things were still forming. Remember that vacuum cleaner? Things are still being basically cleaned out in our solar system. Jupiter is a really good vacuum cleaner. I'll talk more about that in a little bit. So I said funding went up, then funding went down. Where are we now? Well, we're doing okay. And the main reason why people still talk about this, again, we talk about the little ones hitting satellites, talk about the big ones. We want to protect all of us here, life on Earth. Well, here's a general idea about how big things are as a function of how often they're hit. And it's the only plot I have in here, so bear with me. This is how big it is, an asteroid diameter, so 4 meters, okay, up to 9,000 meters, and how often it hits. So what can you take from this very generalized, not scientifically accurate line? The bigger it is, the less likely it is to hit you. And that's a good thing. Now, having said that, Chicxulub, cause of the dinosaur extinction 65 million years ago, we're about due for an extinction class event. And you'll see this in the news a lot. Even accounting for the fact that the solar system is being cleaned out, we have far less objects now than we did before, we're still due. So there are a lot of people, again, looking to make sure that that doesn't happen. Can we build spacecraft to protect ourselves? Can we do something about it that the dinosaurs couldn't do? Most recently, you can talk about the Arizona impact crater. Who's been to the Arizona impact crater? Not too far. Oh, excellent. Okay, so a little less than half of you. Arizona impact crater was about 50,000 years ago. Okay, it was about a 50-meter class event, which caused a crater that was about 1.2 kilometers across. So remember, 50-meter object causing a 1-kilometer dent in the Earth. Tunguska, boy, this is controversial. People will start yelling at each other if you go to a conference talking about the Tunguska event. This happened in the early 1900s. And the evidence for an impact is the fact that there was widespread devastation. Over 80 million trees, over 2,000 kilometers, were basically flattened in Siberia, okay? There's no crater. So you have one person getting up there saying, it was a comet, we didn't know anything about it, this is scary. Another person saying it was an asteroid that just exploded higher up. Other people saying it was aliens. You always get aliens when you're talking about this stuff. Still controversial, but this only occurred 100 years ago. What if this had occurred over San Francisco? Stanford, right? Send it to the East Coast. See, it's funny, whenever you see these disaster movies, it's either like New York or San Francisco or Boston, MIT. So you have to worry about these objects that maybe 50 meters, 100 meters, not going to cause widespread extinction, but can cause devastation locally. Okay, so why do we study these? Well, meteors, again, is one of those topics that a lot of people get interested in. You can study it for atmospheric physics, look at things like temperatures and winds. You can actually look at the plasma formed in our atmosphere and then be able to glean out things about, let's say, global warming, okay? How much mass is actually being put into the Earth system? Astrophysics, like we talked about life on Earth. How did our solar system formed? Why do we have all these big rocks in our solar system? But again, for here at Stanford in my department, we're really focused on mostly building spacecraft missions to go rendezvous. Can we protect our spacecraft that are currently in orbit? Can we build better spacecraft in the future so that we don't have to worry about this in the future? Okay, a little bit more history. Let's talk about the little ones. And I was really inspired by this morning's presentation, our keynote speaker, and how she was talking about creativity and kind of pushing the bounds on what you hear in school. And I think this is a classic example of why we need to do this. Because just a couple hundred years ago, people said there is no way that rocks could fall from space. Aristotle, more than a couple hundred years ago, said it. But then most recently, the French Academy, which is equivalent to our national academies, said stones cannot fall out of the sky. And at the same time, around the same time, Jefferson, very famous quote, "I would sooner believe that 2 Yankee professors would lie than that stones would fall from heaven." So here are the most brilliant people in the world saying, no way, not possible. Very smart people saying this too. They didn't believe it just a couple hundred years ago. What do you think happened to change their minds? Yes? Did everyone hear that? Maybe one fell through their house. Yes, that's actually very similar to what happened. Data over in Europe. All of a sudden, all these streaks in the sky, and people are like, oh, the sky's falling, life's ending, and the whole drama. Lots of meteor showers in the late 1700s, early 1800s, okay? It got to the point where people would look up and say, yeah, there's no way that these are rocks coming from the Earth that are being bounced back up, which was one of the prevailing theories at the time. Okay, so finally people started to change their ideas. A German physicist said, yes, I'm going to propose that these indeed do have an extraterrestrial origin. And then finally in the early 1800s, meteorites were established as distinct from terrestrial rocks, meaning we know they're not from Earth. Interesting, next time all of you are at a museum, try to find a meteorite that dates before this date, meaning found before that 1800 date. It's hard because people threw out their meteorites prior to this because they believed what the Academy was saying. These can't be extraterrestrial, they must not be worth anything. Okay, so next time you're at a museum, try to find something that predates this. It's hard, not impossible, but it's hard. Okay, where do the little ones come from? Well, the little ones actually come from the big ones. Right? So primarily these little ones, again, grain of sand, come from things like comets. There's the Kuiper belt, there's the Oort cloud. The Oort cloud's much further away, 50,000 astronomical units. An astronomical unit is the distance from the Earth to the sun. They also come from asteroids. And where's the asteroid belts? Yes? Close. Yes. Mars and Jupiter, that's right. So it's pretty close to us. And for this reason, we have an ability to keep an eye on it and make sure, again, that those big ones are not going to be hitting us. Okay, showers and sporadics. So again, you have all heard about Leonids and Geminids. When the Earth is going around in its orbit around the sun, every once in a while it will encounter a debris stream that's also been in orbit around the sun. This is what's called a meteor shower. So what happens is for the Leonids, which is host to this comet, Tempel-Tuttle debris, is that November 17th and 18th, the Earth passes through this debris cloud every November, okay? But when the comet has just recently come by and deposited its debris is when we get a storm. And that's when people get really excited because there's fresh debris for the Earth to sweep up. That's called a shower. Again, a sporadic occurs all the time, occurs every day. We always have to worry about it. Okay, so I had a wonderful question before starting. What's the difference between a meteor, a meteoroid, and a meteorite? Does anyone want to take a stab at this one? In the front again? Okay. It's hard. It's hard. And in fact, for those of you who may have heard of They Might Be Giants, do you guys ever hear those? Yeah, those songs? Okay. There's a wonderful song that they put together on what a meteor, a meteorite, and a meteoroid is. All right, and I'm always on my students' case, as Nicholas can attest to, about make sure you use the right definition. Meteoroid is the object in space. Okay, it's the actual physical object. Meteor is the plasma formed when it comes into our atmosphere. And a meteorite is the thing that hits the Earth. Okay? So now all of you, when you go out and talk about this, you can use the right terminology, and we can get rid of these misuse of these names, which is all over the internet. Okay, so you already heard this. 100 billion. How many think that's big? How many were surprised by that number? Most of you. Me too, when I first learned it. 100 billion, think about it. 100 billion depositing 300,000 tons per year. Not a significant fraction of the Earth's mass, but certainly something that we should be studying. Here's the thing that's really interesting. 11 to 73 kilometers per second. Okay, so think, let's say you're going to get to the San Francisco airport, 15, 20 kilometers away or so, maybe a little bit more, in a second. Think how quickly these things are moving. It's almost hard to visualize. It's almost hard to imagine just how fast these objects are going, way faster than a bullet out of a gun. Okay? Because of that, they have an incredible amount of energy. So when they hit things, even if they're not too big, what's going to happen? Yeah, boom, right? Plasma, it's going to be fantastic. So this is what happens when it comes into our atmosphere. Meteoroid gets hot, this very simple cartoon. It hits the atmospheric molecules, and it ionizes them, meaning it's creating free electrons and ions, fourth state of matter. That is actually what you're seeing. When you look up and see a shooting star, you don't see the particle. They're way too small. You're seeing that plasma that can go on for many, many kilometers. That's what we study because it's too hard to actually study the object themselves. So what this means is that we also have to then be plasma physicists and understand if we study this, how are we going to figure out properties of that? Because that's the thing hitting my spacecraft. Okay? So how do we study these? Well, first, you look up. How many have seen shooting stars or meteors? Pretty spectacular, right? They can be. So the oldest observational method then is just visual. This camera, which is now actually on the roof of the Duran building right over there, can give you some images like this. I don't know if you guys can see them, but they're basically just these streaks that come at you. Okay? It's easy. It's an easier measurement. And it tells you roughly a little bit about it, meaning how far away it is, how big it is, how fast it's moving. It can also tell you where it came from by basically triangulating back to a single point. We also use something called radar. What does a radar do? What does a radar do? And you could cheat and just read my, yes, what does a radar do? Excellent, very attentive, I love it, I love it. Tell my 6-year-old if she would just listen to me. Yes, no, perfect. That's right, so most people know about radar because, of course, we use radar to make sure our airplanes are in the place we want them to be. We use it to do weather. Well, we also use it actually to study plasma. So we have a radio wave, and it's an active measurement, meaning we're bouncing it off of something, okay, but we're bouncing it off of the plasma, remember, not the actual meteoroid. And in this way, it's a more accurate description of what the meteor actually is doing versus visual. So if you happen to be sitting at a radar, and I'm going to show you a movie, this is just going to show you basically a little plasma coming through at 2 different frequencies. Let's not worry about that. But you can see it. So here it is. And this is this big radar out in the South Pacific where I was actually stationed for a couple years when I was working at MIT. And it frequently detects these meteors. And it is one of the first radars to give you that 100 billion per day. This you can't see. This is just something that basically the radar can detect. So not visually, only using these very high sensitive, very expensive instruments. We also, so that was optical and radar, we also can go into space and actually study them. One of the ways we do it is actually by being a big target, okay? So we put a spacecraft out there and we make it as big as possible and we say, hit me. And we're gonna count how many of the meteoroids are hitting us. And we're going to try to get a rough estimate where they're coming from by using these different types of materials called aerogel. Okay? This is one of those very famous satellites called LDEF, Long Duration Exposure Facility. But students also get to play in this area as well. So for those of you who met Nicholas, he was manning one of the tables over lunch. We also went to build smaller spacecraft to also say, hit me, but now we want to look for that plasma. So what Nicholas did is he was able to get a ride on a vomit comet. How many of you know what a vomit comet is? How many of you have ridden on a vomit comet? No? Nicholas has an interesting experience where he was trying to figure out, can his screen, which is going to make us as big as possible so we get hit a lot, will actually deploy in 0G, meaning no gravity. So let's watch him. So that's his screen. Nicholas had a fascination with origami as a child. He actually used those skills to come up with different ways to fold the screen, not always successful, always successfully, in this vomit comet as he was being put through these awful parabolas to deploy his screen to see if this would actually work on orbit. As far as I know, Nicholas did not get sick. Did not get sick. I did not go. I would have gotten sick. Okay, big ones. This is where, again, when the news and the media contact me, it's always about, are we going to die because of the big asteroid? It's never the little ones, which frankly I find a little bit more fascinating because we know less about them. But for those of you, again, interested in this, it's one of those topics that seems to just keep expanding. So what do we mean when we talk about those big objects that might hit us? Well, again, acronyms, I'm supposed to avoid them, but I'm going to give them to you because this way you can go on Wikipedia and understand what they're saying. We talk about near-Earth objects and potentially hazardous objects. I love the word, potentially hazardous. Not definitely hazardous, potentially hazardous. So what do we mean here? Well, if it's a near-Earth object, it could be either an asteroid or a comet, and it's basically pretty close. It's less than about 1.3 astronomical units away. What's an AU? 150 million kilometers, again, distance from the Earth to the sun. So we're looking for things that are close by to us, okay? There's about, I just got the statistic yesterday, about 9,000 that we currently know of, and we're tracking them and making sure that they don't hit the Earth. A PHO is one that's even closer, so 0.05, and also it has to be pretty big. It has to be pretty big. This number's a little scary. 1,300 potentially hazardous objects that we're tracking right now. And here's some images of some asteroids actually taken, Itokawa, based on some of these rendezvous missions and also some of the characterization. Okay, so how do we actually study near-Earth objects? Again, we do this optically. And I mentioned funding went down, then funding went up, funding went down. Well, currently there's only 3 systems of telescopes looking at these near-Earth objects. All right. The first is linear. This is at Massachusetts Institute of Technology. And then Catalina, which is based in Arizona, and Spacewatch as well. So linear operates telescopes in New Mexico, and these are operated in Arizona. They're about 1 meter sized telescopes. And I don't know if you guys can see this. It's circled in purple, but do you see that little dot moving across? That's an asteroid. So there are people who are employed every day to look through these optical images and just find those little dots going through and making sure those little dots don't hit us. Radar, however, is the only true way to actually characterize them. What do I mean by that? I mean, how big is it? What's the mass? What's the diameter? What's it made of? We use radar and, again, some rendezvous missions, but unfortunately, less than 1% of near-Earth objects are characterized. Why do you think that is? That's right, they have to be close. Money too, funding too. But they have to be pretty close, okay? Which means it's difficult to actually get some estimates on most of the near-Earth objects. Okay, so how scared are you at this point? Pretty scared? Okay, let me bring it back then, because I don't want all the parents to get mad at me that your children are having nightmares tonight about asteroids hitting the Earth. It doesn't happen that often. But when it does happen, we're usually surprised by it, okay? Impacts in the outer solar system. I mentioned Jupiter is the big vacuum cleaner. Well, a couple of years ago, well, actually 2009 now, an astronomer actually just noticed a dark spot on Jupiter. And then retrospectively, they figured out that a comet 1.5 kilometers in diameter actually hit Jupiter. They didn't know what comet it was. They'd never seen it before, and they certainly had never predicted that it would actually hit Jupiter. Okay? It happens here all the time, too. You can go in the news at any moment and say, such and such asteroid, close call with Earth. You see it all the time. 2009, DD45, about 50 meters in diameter, came within 72,000 of hitting us. June 27th last year, I don't know if you could see this little dot moving across the image. This was a little bit smaller, also came within about 12,000 kilometers of impacting Earth. And then tomorrow, there's supposed to be a close call. When I was looking yesterday, I'm like, what are the odds? Well, the odds are actually pretty good that you're going to have a close call at any moment. So I won't go to the website just because I'm a little bit down on time, but you can go actually to this events.slu.com and actually track this asteroid as it's going to make its close approach to Earth. Now, it's pretty far. It's 14 times the distance between the Earth and the Moon, but look at that size. Look at that size. And also, look at the error on that size. We don't know. We don't really know how big it is. And then the one that got everyone spun up a few years ago, Apophis. Who's heard of Apophis? Oh, only a couple? It's an awesome name. It stands for Apep, which is the Egyptian god of evil and destruction. Yeah. There was, a few years ago, 1 in 45,000 probability that was going to impact Earth in 2036. That probability has since gone down, but it's the reason why everyone got spun up. Let's come up with a mitigation mission. Let's figure out what we can do to make sure that we are not going to get hit by this thing. Right? So what can you do, all of you budding engineers and scientists? Here's some ideas. One, you can shelter in place. If it's small, 20 to 40 meters, you're not going to have a lot of warning time because if they're small, they're hard to detect. So you can evacuate, you can basically hunker down, or you can get some emergency infrastructure put in place before it hits. If you have decades of warning time, you can push it. All right, there's all these interesting techniques where you get close to the object and then you just gently push it or pull it. Okay, you're pushing or you're tugging on it. You're not destroying it, you're just gently moving its velocity a little bit along its orbit. Or you can blow it up. This is what Hollywood loves. This is what you don't want to do, though, for the most part. Okay, do no harm. That's the first thing we were told. You can do a kinetic impact where you just actually send a spacecraft off to rendezvous with it and then shove the spacecraft into the asteroid. Right? Or, here's the big controversy, nuclear. Why is this controversial? Well, 2 reasons. One, we actually don't have enough of a stockpile to actually mitigate the largest asteroids. But 2, we don't want to talk about this because of, remember the do no harm? Yeah, this is controversial. It may be our last resort, however, if there's nothing else that we can do. Okay. And there's always Hollywood. So believe it or not, some of the methodology that we're now exploring was actually inspired by these very bad Hollywood movies. So you always tell children, limit the TV, only watch educational programs. If you're going to pick one, Deep Impact's the best one. It had the best science advisors. And as my intro said, I do TV as well. So again, I tell my children, limit the TV, but I did let them watch my National Geographic show. And I am supposed to host a show on PBS this coming fall called Near Earth. So a little bit of TV is okay. So just in conclusion, meteors happen all around you. There's so much to explore. This particular one was, again, one of these ones that we didn't expect. It was way back in 1992 during the Draconids outburst. And again, it was one of those where people said, oh, aliens are coming, or the sky is falling. Just turns out it was an asteroidal particle going about 15 kilometers per second. So I encourage all of you to get out there, think about how you can study them. There's so much we don't know. Think about what you can do to prevent real-world incidences like this. It actually hit the car of a young woman in New York City. Apparently the car only cost $100, so she wasn't too upset by it. However, it does have an impact, forgive the pun, on all of our everyday experiences, from life on Earth to extinction to satellites. So here's my lab. Thank you so much. Thank you for the opportunity to speak to you.